Ladies and gentlemen, good evening. Thank you for your time, for being here. My name is Yves de Leeneer. I'm the 121st president of IMarEST. And IMarEST stands, for those who don't know, Marine Engineering, Science and Technology. And today, although being a naval architect specialized in subsea systems and hydrodynamics, I want to show you how you can have projects that have both engineering, science, and technology in it. Just to, like my good friend Professor Demore, I would say, be a bit more holistic. So I'm going to talk about reef building and beach protection. So first of all, I'm a naval architect. I'm from Belgium. My mother tongue's French, went to school in Dutch, and obviously I work a bit in English. I've done a lot of engineering, design, project management, installation of FPSOs and FSOs for companies that used to own FSOs and FPSOs. Been 30 years in oil and gas, renewable energies. I was based in Houston, West Africa, Southeast Asia, and now mainly Singapore. For 16 years now, I've been running a small consultancy company called Deep Blue that specializes in subsea systems, mooring systems, etc. And done a lot of offshore installations. So I have the advantage of doing designs, engineering, and then going at sea to see if whatever I did is actually working. What many don't know is that for 10 years, and it's a private thing, I was on the board of an NGO called the Biosphere Foundation, and they specialized in coral reef research around the world for the last 20 years. And about 10 years ago, with the help of Bev McKenzie, I don't know if she's still here, we compiled 20 years of research on coral reefs, and we gave them to the IMarEST. And it took a while, but they went through all the data, and they went through the proposal of the book we had, and they agreed on it. And so there is a wonderful book, which is edited by IMarEST, which is Coral Reefs, a Handbook for the Future. So in general, most engineering projects often have a negative aspect to them from an environmental point of view. Even if you want to do it right, there's always going to be something. So I thought, well, what if we try to mimic the environment so we are less encroaching on with the man-made system and see how we can have less of an impact on the environment. At the same time, I remember Buckminster Fuller. Some of you might be familiar with what he did. He was an architect, and his point of view was whatever you design, I'm paraphrasing here, but whatever you design should have a positive impact on multiple things, from an aesthetic point of view, as well from a social point of view, and a natural environmental point of view. So taking that into consideration, like I said, I've tried to combine engineering, science, and technology here in one project. We said, well, what is being built by humans that is actually has been built by nature before in a different way? And we looked at corals and systems around the ocean. So, and especially in breakwaters. Now, breakwaters are used to limit coastal erosion. Coastal erosion is waves and current hit the beaches, stones, sand, and erode, take away some of that equipment, some of that natural sand. And that's happening worldwide. So we say, well, and people have been preventing it, trying to prevent that for centuries. And so they've done that successfully by putting barriers to prevent the waves to come in, which we've all seen that. We probably fell on some of them when we were younger at sea. And so we have these barriers which are human-made, which are not very aesthetic or beautiful, cost quite a bit of money, and they prevent the waves from passing into a different part of your area. So these are the surface breakwaters. So these are made So you got a wall, the waves are coming, so behind the wall, no more waves, no more current. And here are some pictures of them. Now, they don't look very nice, but they do a great job. So there's a different type of breakwaters, which are the submerged breakwaters, which basically do the same as the other breakwaters, but they don't stick out of the surface. So they stay below the surface, which is nice because you can't see them. And what they do with waves is that they don't completely prevent the waves from going through, but they prevent a majority or the highest part of the wave from going through, and you'll still have some waves going through. And they're placed at a certain distance below sea level. And depending on how deep they are, they work well, they work less. Anyway, I looked at it, well, why don't we do a natural submerged breakwater? Now, the natural submerged breakwaters, I'll talk about later. These are the man-made submerged breakwaters. So this is a breakwater, stone, concrete, whatever. Here again, certain height below the surface. And so waves will come in, some of it will reflect, the rest will go through. So you prevent a certain amount of waves to come through, but not everything. But again, a lot of stone, a lot of things, cost quite a bit of money to install. So I look, well, what are these breakwaters in nature? Well, they're called coral reefs. And therefore you have atolls and things like that, spaces in the world that are protected more or less by the waves because of the coral reefs. So instead of building man-made breakwaters, we said, well, the coral reefs are growing. So can we build something that is partially man-made, partially coral reef? So we said, well, we're going to create submerged breakwaters. And what is required to have a coral reef being built? So a coral reef is made out of marine fauna and flora. Fauna is animals, flora is plants. You need correct water temperature for these plants and these animals to thrive, certain amount of sunlight, certain amount of food. So you can't really control that unless you change the area where you want to do it. What you can control is that, I'm not a specialist, but I think I found out that the greater the area you put in the water, it's called the substrate area, the higher the chances that something's going to grow there. So we said, well, let's get something with a lot of area. Let's get something that where when you start having fishes, they can be protected. They have protection, they can hide. Anyone who's done diving or snorkeling, you know the fish likes to go into little spaces. And let's do something where fauna or flora can be housed, like a support and where they can live happily. So basically, it's an existing coral reef or a submerged garden. So what we come up with is this system here. I think this and this and this is the clearest. The blue part is concrete. Then you have pipes. Why do we have pipes? Well, first of all, pipes are empty on the inside. They're hollow. So that's great for fish or little plankton or whatever to go inside and to be protected from the rest of the environment. That's number one. Number two, they're in all directions. And number three, the surface area that you get from the inside and the outside of the pipes is much higher than what you get from a stone wall breakwater. So we have this breakwater here. So anything you put in the ocean, and people that have ships and boats know that, things are going to grow on it. So here you would have all kinds of barnacles and small organisms growing on it because it's a substrate, they can hang on to it and they feel okay. Now, if I look at this, and let's say this is 2 meters, this is 3 meters length, this is 3 meters length, and this is 1 meter wide, we end up with an area of 8 square meters, which I say here, let's say 3 meters, 8 square meters. and that area is exposed to current, waves, etc. Now, here, if you're inside the pipe, you're not exposed to current and wave, or much less. So we've done the calculations, and we have about 10 times more area for the same size if we use this system or this system than if you use this system. So 10 times more area, 10 times more substrate to hang on to for barnacles, for plankton to come in, for fish to hide. That increases the possibility of having a coral reef being growing up there. Sorry, I'm going on the other side again. So we said, well, yes, we need to build these things and we need to see how they work. However, we put them in the water. So what happens? Well, first of all, you have storms. But remember, we're trying to build a submerged breakwater to block the energy of the waves coming against it, or partially block it, so that we have less erosion on the littoral, on the seashore. So we have to look at, well, what kind of storms are there? So first we look at what we call in the engineering of short term, 1 year, 10 year, 100 year. That's just the probability of that storm arriving in 1 year, 10 year, 100 year. So the size of the wave will increase, because if this is a 5-meter wave, okay, or a 2-meter wave, that sounds a bit normal. Let's see, you got a 2-meter wave, and that probability that you have it in 1 year is there. The highest wave in 10 years will probably be a 4-meter wave or something like that. Then for the 100-year wave that nobody has ever seen, but statistically based on the 1-year wave, they can calculate what the 100-year wave would be. Might be 8 meters, 10 meters, 20 meters, 30 meters, depending where you are in the world. So depending on the location you want to put your submerged breakwater, you need to get that information first. So we also need to get the water depth profile you see here. Here's the beach. How deep is the water? And then we choose a location to put our submerged breakwater. That looks like this, but is probably about 2 meters long, all right? This is about 3 meters high, 3 meters in diameter, and about 2 meters long. So we put those on the seabed, and then we choose a certain water depth. Logically, if you put it in 100 meters water, knowing that's 3 meters high is not going to have any effect on your wave and on dissipating the waves. So you have to put it in like 5, 6, 7, 8 meters water depth, depending also on the wave you might see from a probabilistic point of view. So the other important part is the geology on the seabed. Is it sand? Is it mud? So we have to look at that, because sand will move, mud won't move, but sand is being picked up from the seabed with the waves coming through. And sand, also called sediment, well, sediment is just a particle that moves through it. Could be sand, anything else. But so the sand will move around. So that's important also from the beach protection and to prevent erosion. So the other thing to look at is, if you build something and it's not heavy enough, logically it's going to move on the seabed. If you have a 100-year storm, which let's say it's a 6-meter wave, the forces from that wave is going to pick up whatever you've put on the seabed, and it's going to move it around. And if you start having coral there, then it's going to get destroyed. So you need to look at the on-bottom stability, which is things we do on a regular basis when you do subsea designs. And based on the location, the metocean data, the geotech data also, because if it sinks in the seabed, it will be more solid than if it doesn't. And we look at all this, and then we come up with a system that is suitable. Like I said, it has an impact on the beach, on the erosion of the soil. So if you have, when you have a wave passing through, when you have a wave passing through, it will pick up some of the soil in shallow water that's on the seabed, and it will move that around. The higher the wave and the more the energy of the wave, the more soil it can pick up. Now, if you put a breakwater in between, some of that energy will be lost, and so some of the particles that are traveling with the wave will drop behind the breakwater because it doesn't have enough energy anymore to carry those particles. So there are, Anna knows better than me, there's a lot of software available to calculate that. And so we can have a pretty good example of what's happening to the soil and what's happening to the waves. Now, the waves, it's not too complicated. So this is an in-house program we have. And basically what it shows here is that we took one of those breakwaters with all the tubes, and we've put a 2.5 meter wave in 4 meter water depth in a period of 6 seconds. And the initial wave, which is the red one, had a certain wave height, which was, no, it doesn't, oh yeah, wait, this is here, 1.5, so 1.2 more or less, and the trough was saying 1.2. Sinusoidal wave, not realistic, but good enough to have an idea of how much your wave will change. And so we put the system in 4 meter water depth with that kind of wave, and then what happened is that that's the new wave that we got, which is attenuated. And from a height point of view, the new wave was 0.8 of meters. So that's a reduction of 70%. And the wave energy was reduced by 90%. So that has a big impact on the waves that are now hitting the seashore and the beach. They won't be as high, they won't be as strong, so less erosion will happen. So to use one of those softwares, you put your submerged breakwater here, the waves are coming from here, and then this is what happens. There's some turning around from the waves. So that's the wave pattern that changes, and that's the sediment transport, how the yellow is extra sediments. So this is extra sand that has deposited itself behind the system. So I had a video here, but we couldn't show it. But basically, we've looked at the second thing to look at is at the structural strength, because those pipes have to be strong enough so that a 100-year wave is not going to break them. So you can see here, this is a stress plot. So we ended up at 107 megapascal stress with a pretty high wave, although it's not given here. But so we looked at, well, first of all, is it going to be stable on the seabed? Secondly, how are these pipes doing when the wave passes? Are they breaking? Are they not breaking? So once the design is completed, we've built molds, and basically we either build them in Singapore, wherever we want to build them, because the molds can be sent easily by container, so we can send them all around the world. And depending on how big the project is, we like to stay in control. So we build them in Singapore, and then we ferry them, well, not ferry them, we container them and send them everywhere. But if it's a much larger project, we do it locally because it's cheaper. So then for the offshore installation, there's different ways depending on how much money the client has. We can use barges with cranes on it, or cheapest way is to use empty 200-liter blue barrels, fill them with air, and have these systems have the concrete part of the system, which is this part, have that part slowly pushed in the sea, in the sea, and with local divers put it 100, 200 meters away wherever we need to put them. And then the pipes can be installed at a later stage. So also what we do is we need to prove our system works really well. And all you've seen before are simulations. So we need to prove it to the client. So we just use standard wave buoys. We put 1 or 2 behind the system, and we put a few in front of the system or laterally where there's no obstruction. and we can easily see the difference in wave height and wave energy passing through. So what we also do then is a yearly assessment, because the idea, as you remember, is to have a coral reef or a kelp garden being built. And we are specialists that run transects. Transects is just areas with they dive and they use a lot of lines in squares, and then they calculate the amount of coral, fish, plankton within that square, and then you can multiply it for the total area that you have. And that you can do with local universities, aficionados of scuba diving, students, whatever. So this is the result we got after 1 year. So this is a coral, as you can tell. This was in Dubai, and this was probably in the beginning. So what you have is you have plankton that starts getting on the pipes. The plankton attracts the small fish. The small fish attract the bigger fish. And after a while, you end up with quite a bit of growth on your system, with the idea that this is after 1 year, that after 10 years, it's completely filled up. And so what you have built is actually only a skeleton, and the rest is filled up with coral, and the coral takes over. You've checked that it's stable, because the problem is if it's not stable on the seabed, if there's a big wave, you can have a lot of coral growth, and then there's a storm coming and the whole thing moves away, and you've lost what you had. So most things in the offshore world and oil and gas, and even in the marine world, have a design life of 20 years, sometimes pushing it to 30 years. That's because of corrosion, because of fatigue, because of all kinds of different things. Here, what is great is that we don't really care about the design life, because after a few years, it becomes a natural product. And in a way, it has an unlimited design life. Now, this was in Norway. So you see, there's not much coral reefs in Norway. Well, there might be, but not in the cold water where we were. And you see, there's a lot of kelp that grew. So this again, this is after 3 years. We start seeing all kinds of, this is in Norway again. So this kelp was this originally, and zoomed in a bit. You end up with, you can hardly see the structure anymore. And then this again is in Norway. And we start seeing all kinds of small animals coming in. So to summarize, the system has the same advantages as a conventional system, because it reduces the wave energy, the current speeds, and the beach erosion. But at the same time, it promotes growth of coral reefs and kelp, and in general, marine life. If you look at the different designs, it is clear that the amount of stones or concrete required here is much larger than the amount of concrete we use here. So it not only does it has an environmental advantage, it also has an advantage that we need much less rocks and everything to build it. Much less concrete also, and it provides a good waves and current flow for the small marine life, because it's the hollow pipes provides housing. So no large boulders or rocks are mined, which is often the case when you have a traditional breakwater. The concrete used, if you make the breakwater out of concrete, we only use 15% of the concrete you would use for a similar size breakwater. The environmental impact is therefore positive, and because you create a new garden, you create coral and environmental life where there might have been nothing before that. The substrate, the area, again, is 10 times that of a conventional breakwater, more or less. And also, although there's a lot of controversy about my next statement, some people, some environmentalists and scientists say that coral reefs are a carbon sink. And this is the number I found online, about 0.15 tons per square meter. Others say no, because it will release the carbon at a later stage, so it's not a positive balance. But anyway, it's a good thing that it takes for a time, it takes some carbon in. So with time, the breakwater is covered in coral and kelp, and it becomes a solid reef and garden. So you've created something new, submerged. And the cost in the UK for a submerged breakwater is about between 5 and 10,000 pounds per meter length. And that the reason for that is that you need barges that can dump rock and all kinds of things. In my case, the cost is much, much less. You still have a cost because you have to install it. That's actually your highest cost, is the installation. It's not the fabrication. Now, there's other applications for it. Here we looked at a submerged breakwater to prevent erosion. But as I explained, because of the reduction in speed of the water particles that have sand in it and sediment, when the energy is less and the speed reduces, the heavy parts of the sediments, the biggest grain of sand will drop behind the breakwater. Now, there's this thing called scour in the subsea world, where when you put something in on the seabed, and with the current, you're going to have different pressures all around it, and that creates a scour hole. So you're going to have a little hole, can be depending, the depth of the hole depend really on how big the diameter of your system is, and also the speed and the current speed and the wave speed. So if you put these things all around, what happens if you calculate the right distance? You have particles moving with the waves. They hit the submerged breakwater, and then some of the particles will drop because the speed of the wave and current has changed. And so instead of having a hole, you could end up with the opposite, which is you end up having a lot of sand around these places. So that's one way it can be used. And of course for fisheries, because fish love kelp and all that, and they can hide in that. So this is in Norway where we installed it, and you've seen that picture before. I've showed you before. This is in Norway when we installed it, and this is all the kelp that grew on it after about a year. So that's about it. Thank you for your time, and if you have any questions, please feel free. Thank you.
Thank you, Yves, for a very informative presentation. I enjoyed that very much. Just a small question. I wondered, earlier in the presentation, you mentioned that about 90% of the energy is absorbed by that structure. Has any thought been given as to how some of that energy could be recovered, perhaps for renewable energy purposes? I know it might be difficult with all that marine growth, but I just wondered if there might be an opportunity there to recover that.
No, I'm not smart enough for that, number one. Secondly, to gain that energy, as we have a specialist in the room called Martin Murphy, he worked with wave energy recuperation for many years, and he will tell you the problems he had and the successes he had. But no, my idea is it's more from, first of all, wherever a breakwater is going to be built, let's try this because it's environmentally nicer than just dumping rock. Because the rock, remember, you have to take it somewhere. So you destroy wherever you take it from, and then you dump it somewhere else, and you destroy where you dump it. So there's two destructions going on. So this is less. You still have some destructions because it's concrete. But so the idea is to try to use that instead of dumping rock, especially that it's much cheaper as well. That's number one. And number two is to promote the coral growth, especially in places like Indonesia. Not much coral. There is coral in the North Sea, but not much, and probably at much deeper water depth that I know. So the idea is to help economies that are living off tourism to, first of all, protect their beaches. Secondly, you create a coral reef, so you create something for the tourists to see with snorkel, with this and that. So the idea is really that, all right, instead of you have a protection, but on top of that, you create extra marine life, which is great, because there's not enough left, because we've eaten it all. And then on top of that, we attract tourists because you end up with a coral reef garden, basically. Yes, Barry.
Fascinating talk. Fascinating talk, particularly where you've set the scene of engineering, science, and technology coming together. Two questions. What actually is patentable within your concept there?
Well,
secondly, set the scene for this. We hear a lot about bleaching of existing coral, particularly the Great Barrier Reef. Is there an application for this to help save that particular coral?
To your first question, it's still, I've paid for the patent, so I think I have another year where they're going to decide if it's patentable or not. That's number one. But anyway, with patents, the good thing to have a patent is that it looks serious because you have a patent. Now, if somebody wants to copy me and I have a patent, what can I do about it? I have to spend hundreds and thousands of dollars in lawyers if I want to fight them. So anyone who wants to copy it, feel free, because it's I can't fight it unless I spend a lot of money on lawyers. So there's a problem with the patent. It's good to have, but you need the means to protect it, to fight it. That's number one. Number two was about the bleaching, correct? Yeah, no, it doesn't help you with the bleaching. What it can do is that, so bleaching happens, as far as I'm concerned, and I understand, and the marine biologist will contradict me if I'm wrong, please. Bleaching happens because of high spots of temperature in certain parts, and it moves around the world. So what you could have is that for a year or two, you have a whole set of coral that's been bleached, but then, because of El Nino and all that, I understand, but then maybe the environmental situation that made it bleach disappears temporarily or moves away, and then you could use that to recreate coral.
Good evening, sir.
Evening.
Fascinating lecture.
Thank you.
Just one small point. With the tsunamis which take place in Indonesia and all that part of the world, would that affect your structures?
Yeah, in a positive way, because the government would have asked me to restart again because they would have been swiped away. So no, there is a limit that I can build against tsunami, but it's going to be so expensive that, in every engineering, there's a limit between what's possible. And normally the insurance companies do the same calculation. And any event, well, that's from a few years ago, maybe has changed now, but any event that has a probability of less than 1 in 10,000, we assume it's not going to happen, because the cost to make it, the probability that it's going to happen is 1 in 100,000 is so much higher than the cost of insuring the item itself.
Thank you very much.
You're welcome.
May I?
Sure.
Thank you, Yves, and thanks for the plug about wave energy. But just to go back to the comment about renewables and trying to use the kinetic energy of the wave, there has been experience over recent years with near shore wave energy devices trying to do just that, which will have that impact of reducing the impact of wave on shoreside and erosion. But the classic problem with wave energy devices is the kinetic energy and converting that energy into usable electricity, and that problem goes on. But if I may, a question for you. I'm really interested about the prospect of using the devices around wind turbine towers, which are fixed bottom installed on the seabed. One of the classic major problems that offshore wind turbines have faced is scour, as you've described, and particularly where the cable comes off the tower and taking cable to shore, and the wear on cable, which has caused a lot of insurance claims with respect to offshore wind installations. So I wonder if you feel that there's real scope for that. Has it been tested with any manufacturers of wind turbines? Because I think that could have a real prospect.
All right, thank you very much. No, it hasn't been tested with the wind turbines. And when you talk about, so I was talking about the scour that you would have around the monopile of your wind turbine, but you talk about the scour around the cable, correct?
Yeah, the J tube, which typically
All
comes
right,
off the
okay.
turbine.
So that part of
takes the
the, that comes out of the J tube or all the way the cable or just that part. So for that part, normally you have pipe shield that makes those artificial seaweed maps. I don't know if you're familiar with them,
Yes.
which normally breaks quite a bit of the scour by doing actually the same as what I'm doing, but I haven't tested it yet, but we'll speak again. Thanks, Martin.
Thank you, Yves.
Thank you very much, Yves. That was fascinating. I might have missed it, but you said a number of times that the hub of your little hedgehog is concrete. Did you tell us what the pipes are made of?
No, I didn't. A reason for that, because it doesn't sound good. So,
Well, in which case, a secondary part of the question would be, if it isn't so good, are there material science developments that could encourage different species to populate the structure
sure.
in different things? Go on, give us the bad news.
All right. So now I'm using, how do you call it in English? The pipes that come off your toilet. How do you call that? The corrugulated pipes. Yeah, the corrugulated pipes that is like corrugulated means it goes up and down. And the beauty of the corrugulated pipes is that the plankton has so many places where to hide. So they work fantastically well. First, we had smooth pipe. They're made of plastic or polyurethane or whatever. And we had the smooth pipe didn't work so well. So we had to use a grinder and make cuts in the pipe for the plankton to connect better. So then I found these drainage pipes that work really better, and they're really cheap, and they can be fabricated anywhere. Every country makes them. But it's plastic. That's a negative. So we started looking with bamboo, and the problem with bamboo is that it's smooth. So again, I have that problem. I need to rough it up. So and bamboo works, and it's nicer. But now we're looking at, there are new plastics that are made. It's not really gelatin. I don't know what it's made of, but it's a natural product. It's not a petroleum product anymore, but it behaves more or less like plastic. So we're looking at seeing if some of the pipes we can find standardly made based with that kind of material.
You need something that's rough if the substrate. I'm just wondering, because I've heard that there are some fairly unpleasant materials that some marine species love. And I'm wondering whether, you know,
No, I didn't look at that. I didn't.
I think there's great scope.
Yeah, it's like I say, I'm a naval architect specialized in waves and hydrodynamics, and so it's very interesting for me to do other things also, and that's why I wanted to present it. But yeah, no, I need to hire a professor here, one of the few professors in the room, to help me out with this.
Yves,
Yeah.
Going back to the hedgehog
Sure.
and the concrete part,
Sure.
rather than manufacturing it, did you consider reusing the likes of the concrete mattresses from the offshore?
From the oil and gas.
Yeah.
Yeah. Well, depends where you're in the world. If you're in Asia, nobody will recuperate them because it costs too much money to pick them up, just in vessel time and vessel fuel and manpower. A concrete mattress probably costs the standard, which is what, 6 meters by 4, probably costs £1,500 in Asia per concrete mattress. Now, just the hour or the half hour required to pick them up with a crane on any kind of vessel is going to be £10,000 per hour. So it doesn't make economical sense in Asia. But I'm sure here you can't leave them on the seabed, so you probably have to lift them up. And so here, yeah, but I'm not a specialist in concrete. So how do you destroy concrete and make it new again? That's my next question. Is that possible? I don't know. You do, all right. So I think there it's going to be, if it's environmentally very interesting for the company, yes, of course. But then I'll go to a concrete specialist and say, you give me the concrete, but it has to be environmentally positive concrete that is recycled.
But as it's already been under the ocean, you might not need to actually recycle it. Just it would maybe change the shape slightly because they're not as solid.
Oh, to use it. Okay, okay,
Yeah.
okay. No, but it wouldn't be heavy enough. I need about a ton of concrete, and I don't think mattresses are that heavy. So I could maybe have 2 mattresses or 3. It's something I can look into. Yeah, definitely. Yep.
Yeah, if you mentioned about mid-ocean data.
Sure.
I know you're an expert in that area. Can you talk us through how these data can be translated into some source of data for offshore winds, performance?
All right. So everything you put underwater is going to be impacted by current and by waves. Current is normally tidal quite often. So there you get, and anyone who has been on a ship or a boat knows there's tide tables and current speeds and all that. When it comes to waves, most of the time the waves that we deal with are wind driven. So it's the wind who blows on the sea surface that creates the waves. And so there's a direct correlation between wind speed and wave height. So that's why when there's a storm, there's a lot of wind and there's a big waves. It all makes sense. So what we do, and it's with the satellites being cheaper and the data from satellites being more available, you can do 2 things. You can go to the NOAA from your country, and you have free data on satellite data of wave heights, but you need to log in and you need to become a member, and then it's a bit messy to understand the data. So if you don't want to do that, you pay. The French company I use that used to charge me €3,000 and would give me a pretty good 1 year, 100 year, 1,000 years storm scenarios with the wave height, the average period, because a wave has a speed, which is linked to the period also. So for about €3,000, I would get preliminary data that I needed. The problem is that if you're in Indonesia, there's not enough satellites, because there's nothing really interesting there. So the satellites, when I say satellites, I mean the satellites can measure the height of the waves nowadays. And so they measure the height of the waves for about a year in a certain area. And once they have that, we can with statistical functions, we expand the average waves for 1 year or 5 years to 10 years, 100 years, 10,000 years. Does that answer your question? Right. Thanks, Leeneer.
Good evening, Yves. Coming back to the question of extreme waves, for most conventional rubble-mounted breakwaters, the easiest solution if something breaks is go and drop a few more rocks there or go drop a few more tetrapods there. Whereas, let's say if something goes wrong in your system, potentially you're losing multiple of these large units. So you might have to remanufacture them. Is that some sort of a conversation that comes up when you talk with, let's say, local governments, and they say that we don't know if these units are huge, and if we lose one of them, then it's a higher cost than us just simply dropping a few rocks or dropping a few tetrapods or something like that?
Well, that's because the people that drop rocks haven't worked in the offshore industry. In the offshore industry, you need to calculate that it's not going to go wrong because the impact is hundreds of millions of dollars or even more. So like I said, we do an on-bottom stability check. And well, I didn't go into detail, but if there's a limit at which the amount of concrete you can put is there. So a good size is 300 mm, 30 centimeters, or about a bit more than a foot for the Brits. So you have a foot of concrete, and that gives you about a ton weight. Now, sometimes I needed more. I needed 3 tons. So I looked at it, although I have a mold system that I can change the thickness. It didn't make any sense because it cost more money in supporting and installing. So what we do, if you looked at some of the so here you can see it dry. This was our first design, which was complicated because the molds, so you need an inside mold, an outside mold, and then pipes. So when you pour the concrete, there are holes in it. So That mold is for the moment still in Norway, and I haven't brought it to Singapore to let it like it. So if you look here, it's not, this is the one right here. Here it's not round anymore, it's an octagonal, which is much easier because the mold is made of plates. So I have an outer plate and an inner plate, and I'm just connect them together. So I can change the thickness of my system, but at the same time, if I take you see this hole and this hole are on top of each other. So let's say we've installed it cheaply in Indonesia with the local guys, and we've managed to float it with empty drums. We've managed to float it in the location we want it. We drop it, and this is down the seabed. But I know it's not going to be stable if I got a big storm coming. So what I do is I can go straight through with steel, with a bit of steel here, and I can anchor it. So there I make sure, and that again I can calculate easily. How based on the soil data I have, how deep do I need to go? Now here you see another solution we have. This is gray and this is red. The red ones are steel bars. So the steel bars, because if this is plastic, you have the load coming here, of course, there's going to be, this one's going to try to get out, and this one's going to be extremely highly loaded. So we put steel instead of using, so that's a different way of doing it.
Right. So
So my idea is that once it is sold, it's never going to move. Unless, like the gentleman said, there's a tsunami, and then it's an act of God, and the insurance will cover. Or not cover, whichever.
So you've already planned for having some sort of like a mooring system to hold it in place.
Yeah. So I'll calculate based on the data I get from the 1 year storm, 10 year storm. So I'll build it for the 100-year storm, and that's good enough, because that's what we use in the offshore world where there's billions involved. The 100-year storm is our limit at which it has to work. Now, if you have a 10,000-year storm, it might move a bit, some pieces might break, but then we'll see.
Thank you.
It at the end of the day, it's not going to create a pollution or kill people, so it's acceptable.
Thank you.
You're welcome.
Hey, small question. Once the system is put in place, how long does it require constant monitoring before it can be completely independent?
It doesn't need any monitoring. The constant monitor, well, I say constant monitoring is maybe once a year. You send a bunch of students that have nothing else to do than to dive, and they can tell their prof where we're doing something scientific, and basically they're flying to Bali to get drunk and have fun. But at the same time, they will dive on this, do a transact, and get data, and then they'll give me that data. So I'll buy them a few beers. They'll give me that data, and then I can prove to my clients, look, this is how it's working. And I got the students from Professor Demora proving that it's okay. And there you go.
Thank you.
Hello, sir. I was just wondering that since your design was originally created to limit erosion on the coastal areas, and that the design also deposits sediment behind it as waves come onto it, is there perhaps the possibility of it reversing erosion on shorelines?
Well, in the best of worlds, of course. But you also have this thing called the longshore transport, which Dr. Anna knows much better than me. So now we have, I'm talking, so here's the coast, and the waves are coming like that. But there is an erosion happening, which is longitudinal to the coast as well. So that I cannot really help. She will explain, because I don't really know. I think that's why they put some breakwaters are parallel to the coast, some are at 90 degrees to the coast. And I think one is for longshore and one is for the direct erosion. So these are two complete different things. And it takes, so yeah, in a perfect world, yes, it will increase. But then you're going to have a storm that's going to decrease it again. And so and also you have that longshore transport, which we haven't looked really how that impacts. For the moment, we're looking, well, it has a lot of positive impacts. And yeah, in some places, it might maybe keep it neutral, zero, that we're not building up. Also, the place where you're going to build up. So depending on how deep your water goes and the gradient at which it becomes deeper, your item is going to be put in a certain water depth. That could be 100 meters from the beach, could be 20 meters from the beach, could be 300 meters from the beach. So it's logic that if I have sediment transport behind my system, but I have 300-meter beach, it's going to fill up maybe 20 meters behind, but never the 300. So it's really on a case-by-case basis. But for the scour around the monopiles, for the windmills that are not floating but on the seabed, that's the idea, that you calculate how far you have to put them to make sure that whatever sediment is moving, when it's hit the system, some of it drops behind, and instead of having a hole created by scour, you start having a monticule or a heap of sand around the system to give it more stability. All right.
Yves, very interesting, groundbreaking stuff. Just short questions from my side. First of all, I really don't see why you're considering the 100-year wave scenario when this thing in a couple of years is going to weigh tons with all the growth that it's going to have on it. It's probably going to be immovable at some point, probably a lot better than a standard wave breakwater. My question is coming from a place of tourism, that it's very interesting to try and understand what is the amount of help it offers local biodiversity. Because if you build it along the coast and it's going to be that long, I think it's probably going to have a very positive effect. I mean, I know the company is only 16 years old, so it's a short period of time to estimate that. But are you taking some data on the biodiversity and the growth that it has caused over time?
No, and what you're saying about but I agree. But what you're saying about the 100-year storm is I bought the company about 10 years ago, about 8 years ago. It was a Norwegian company, and they did what you see, they installed it in Dubai, around the Palm Islands. And then there was a big storm, and it got all destroyed. So you have to look at the 100-year. Now, looking at the 10-year storm and the 100-year storm, there's not that much difference. And if you tell a client, oh, it works for the 100-year storm, they're okay with it. If you say it works for the 10-year storm, they're going to have a lot of questions. And the wave height difference between 10 and 100 is sometimes 20%, 30% only. So the total amount of equipment, concrete design, the difference in design is minimal compared to the psychological effect that you tell the client it's okay for the 100-year storm. And the other question was, how long is it long time? Well, that's all the data I have, because after 3 years in Dubai, it got destroyed. So now I'm working in Bali, and I'm looking at convincing the local authority that I can install this. I haven't convinced them yet.
You partly answered the question. It's, how many sites have you got the system installed, and how many kilometers you've installed, and how many years in place, and so on? So
we had 2 places in Norway. But I haven't heard, because I'm not in contact with the original people that were Norwegian. They put it in Norway. We had the site in Dubai that got destroyed. So Dubai is not impressed with my system, unfortunately, because it got destroyed because it was set up without thinking. Well, if there's a storm, how much does it have to wait and all that? So now I'm trying to install it in Dubai, in Bali. The main reason for that is that you need, like you said, how many years and all that. You need an official set of data in order to have more success. And here the idea is that I'm dealing with the Indonesian government. So I'll pay it all myself. You look for about 100 meters along the coastline, built in Bali with cheap labor, with the villages basically that are close by, because I say cheap labor not in a negative way, but you want the local communities to be able to build it, and they can then build it, and if I get a piece of it, I'm happy, but it's basically from an environmental point of view. So I would build it with the locals, and to build about 100 meters long, it'll cost me about $80,000. So, that more or less, and that's by using the students, all right, and doing everything as cheap as possible, because remember, it's between 5,000 and 10,000 pounds per meter for a submerged breakwater. Here, if I do 100 meters for $80,000, I'm looking at 800. and I'm probably still making a profit a bit because my business class ticket is in there, and so it's so you're right. So it's still and that's what I'm working on, just to get the approval. But it's difficult to get approval, but I have people working on it right now.
So it's still early days in terms of.
It's still early days to do it properly. Yes.
Okay,
So it
thank
was
you.
done a bit amateurish before, and the impact on that is that nobody was interested. So they tried to sell it, but what proof do we have it's going to be okay? Oh, trust me, it's going to be okay. Well, the usual last words. So I said, okay, I'll take over and redone it, and then COVID happened, and then business went down. So I haven't been investing anymore in the system. That's it. But if IMarEST can sponsor it, by all means. Yeah. Yes, Ganesan.
You mentioned the project that you did in Dubai was not so successful. Could it be secured by driving piles into the seabed?
Yeah, definitely. But you don't even need to go that drastic. So what I propose to do is have steel tubes, piles, or concrete tubes, but you only need a hydraulic, a subsea hydraulic hammer will be enough. You don't need a big barge with boom 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 piling equipment. But if you need to, yes. But I think that's an overkill. We could do it simpler and cheaper. Now, if Malaysia and the Malaysian government, with whom I know you are very well connected, if they're interested in that, by all means, No more questions? Well, I thank you for your attention and have a great evening. Thank you.